Okay, today, computer scientists, we are going to cover Boolean Zen and De Morgan's law. It's about adding elegance to your code. So first off, we use the word Zen. What is Zen? From the Stride Layman's Dictionary, which is an official dictionary, by the way. Not. Zen is being at peace with total and complete simplicity. So I always think of Zen gardens. So if you go to Japan, you might see a bunch of sand gardens that have been raked with rocks, trees, and moss. Very simple, peaceful. So how can we put this to practice? I want you to take a look at this code. This is a method that is supposed to generate a random number, either 1, 2, or 3, and then it returns that value. Want you to take a look at this and tell me what you think is wrong and how you would improve it. Go ahead and pause the video if you would like a little more time. Okay, so we see that we're generating a random number, we're assigning it to an x, and if x is 1, we're going to return 1, else if x is 2, we'll return 2, else we're just going to return 3. It seems to work just fine, but oh, it makes me so sad because it's so complicated for what we could be doing. So let's take a closer look at what we could be doing. The same method, what we could do is we could assign x a random value 1 to 3, and instead of doing any if statements at all we do is return x. And if we want to get even simpler, all we do is return the value that is generated by the random number generation. Look, less code, more simple. Zen. Let's continue. All right, here's another method. This method returns a Boolean value if two integers are equal to one another. This is a very common beginner's code. So if A is equal to B, we return true, otherwise return false. What could be simpler than that? Mr. Stride, there is nothing less complicated than this. And I would say, you are wrong. We need to get to Zen. And what we need to do is we need to think and know and remember and utilize that Boolean is a primitive type. It is what we would call a first-class citizen. I know it sounds funny. First-class citizen in Java. So A equals B is a Boolean expression that returns a Boolean value, which is the same thing that we are returning. So a simpler way is to simply create a Boolean value result that is equal to the Boolean expression A equals B. And then we return that value. And if we want to get even more simple, Mr. Stride, can we get more simple? Yes, we can. We simply return A equals B. In fact, we don't even need these parentheses here, but I like to use them to sort of set it apart as a Boolean expression. Can you feel the elegance? Can you feel the Zen? Yes, no longer will any of you ever do code like this. And note that sometimes you will return false and return true here. It might be swapped, for which it's simple. You would just put nots, a bang in front of here, and it could still work. You can still do Boolean Zen and have simplicity and peace in your life. So now we're going to move on to something called De Morgan's law and something called a truth table. What we have here is a truth table. I got some columns. I got a variable A, which is true, true, false, false. That has all possibilities of A. And I got a variable B, true, false, which means I have all possible combinations of A and B. So you can see that when I have the two paired together, there'd be 4 combinations: true, 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 false, false, true, and false, false. So these are all the possible combinations of A and B that are Boolean values. What I'm going to do is I'm going to have an expression, not parenthesis A or B. So this is an expression. So A or B, if I take A or B, that would be true, true or true. So I get true or true, and not that value gives me false. So what I want you to do is I want you to complete this table by filling in the values. We have 2 Boolean expressions here. Go ahead and take a second and fill them in. You can pause. All right, here we go. So when we fill them in, what we see is that the right 2 columns are identical.
I think not.
Oh, I want to hear it again. I was talking.
Coincidence? I think not.
Yeah, Coincidence? I think not, right? The fact that these columns are identical is entirely not a coincidence. In fact, it is De Morgan's law. And these two expressions here are identical, and I'll show you how. So what we want to do is, what we're going to practice one more time. Can you find an expression that is identical to this one? And then what you do is, if you find an expression that's identical to that one, you put it here, and then you would test it out by completing this truth table. So instead of me telling you what De Morgan's law, I want you to see if you can figure out what this expression could be equal to. Okay, go ahead and pause the video and try it out. All right, let's see. You may have come to the conclusion that this expression is the same as not A or not B. And how we get to that, I'll show you in a minute. But what we can do is we can fill in this truth table, and we see that these are absolutely identical. So Mr. Stride, how did we get from this expression to that expression? Can you please tell me no? Tell me no. Let me know. I need to know the secrets. And here it is. De Morgan's law works like this. You take the negation of an expression, or the negation of an expression, can be accomplished by negating the individual terms and swapping the ors with ands, and swapping the ands with ors. Or, you know, another way of looking at it is kind of like in math, when you distribute a value in an expression. Here we would distribute the bang and then flip the logical operators. So I know it's not very clear, so I'm here to help clarify. So let's take this expression right here. In math, what we could do is this bang, if this was like a multiplication, we could distribute this to all the terms inside of the parentheses. And as we do that, what we do is we flip all the logical operators. We would actually flip all the comparison operators as well, and that'll come later. So what that means is when we distribute the bang here to A, we get not A. And when we distribute the bang to B, we get not B. And then we switch or flip this logical operator or to be an and. So what we could do is we could say that A is old. I'm going to represent it with old, and B is a teenager. So here I could say, if you are old or a teenager and you're not that, that's the same as not being old and not being a teenager. Mr. Stride, you're still not very clear. This is also confusing. Well, let's keep going. Okay, we're going to do an example here. I'm going to keep with the A is old and B is teenager. So if I have this expression, A and B and not that, I could basically apply the De Morgan's law by distributing the bang and flipping the logical operator. So when I distribute the bang to A, I get not A. When I distribute the bang to B, I get bang B. And then I flip. So how does this read? This up here says, I am not both old and a teenager, okay? I am not both old and a teenager, but I might be one. In other words, I could be a baby, or I could be just a teenager, right? And that will work. So I am not old, or I'm not a teenager, but I might be one or the other. Do you see how these are identical? Let's try another one. A different expression here. If I want to apply De Morgan's, if I want to read this first, I would say, let me take the expression inside of the parentheses and says, am I old or not a teenager? No, I'm not that. Am I old or not a teenager? I'm not that. It's still kind of confusing, but what we can do is we could distribute the bang, flip the operator, and what this says is I am not old and I'm a teenager. Isn't that so much easier to read? Now, so all of a sudden, De Morgan's law seems to have some practicality here and bring a little bit of clarity to this expression that seems a little bit hard to understand. Let's do some more. Let's take this expression here. How would I use De Morgan's law to simplify this logical expression? Well, I'm going to make sure that I have parentheses here, which I do, because that'll help me treat each term individually and do one at a time. So I'm going to distribute the bang to the A. I'm going to swap the or to an and I'm going to put this bang out in front of this parenthetical statement here, or this expression here. Now I'm going to take another step and I can distribute the B or the bang to this expression. And so I can say, well, it's not B, flip the and or, and distribute the bang to the C, and I got just C, because not is just, it disappears. It's like negatives and negative, negative and negative is a positive. So then I have this expression, and that becomes a little more simple. One more. This time we're going to use relational operators. It's the same expression as I had before, but I'm going to distribute this. This looks like a pretty complicated expression. What I'm doing is I'm negating with this first bang out in front this entire expression, and I'm going to distribute the bang and flip all the operators as I go along. So the first thing I'm going to do is I'm going to distribute the bang to the a equals 5. Now, just to make sure we're clear, I'm going to put that a equals 5 in parentheses. When I distribute the bang over here, I have to flip this operator to an and then I put the bang in front of that expression. Now I'm going to apply the bang to this expression here. This expression here on the left, I can also simplify by saying, maybe this could be read easier as not equals 5. It's important here to have these parentheses here because this not is a unary operator and it will get applied directly to 5 instead of the Boolean expression. So by having these parentheses here is important, and then it reads better just to put a is not equal to 5 because that's our intention from the very beginning. Over here, when I distribute the bang, I'm going to put the bang in front of this. Again, I add the parentheses, I flip the and then I put the bang in front of the bang, and I got bang, bang. Okay, bang, bang. Now, one more time. When I apply this bang to this, I would flip the operators. So less than or equal to's becomes greater than or equal to's is how that bang gets applied to this expression. Here, when I got bang, bang, that goes away. So this expression down here is identical to this expression up here using De Morgan's law. Okay, take a second. You can convince yourself through some trials by testing it out that this expression is identical to this expression. Switch gears just a little bit, and we're going to talk about logical operators. You can see that sometimes I want to do A and B. This means A, that means both A and B, and I'm going to assign that value to A, but I can do a shorthand operator, and I can do A and equals B. And here, if I want to do the or, I get A or equals B. Note that there's only one ampersand and one pipe in here in these expressions. So this is shorthand operators for doing this type of thing. Would you ever do this? Occasionally you do when you get tricky in your code. It's not very common for beginning programmers, so I was a little reluctant to show you this, but here it is for those that want to get tricky in your code. And if you ever see this in the future, then you'll know what it means. Here is an advanced application of Boolean logic using the shorthand operators. Can you see that this first statement here is identical to this statement here, which means if B is true, I don't care what A was before, but now I want it to be true. So if B is true, I'm going to OR it to A. If B is true, that means A would have to become true. Boom. If B is false, well, it depends on what A was, and I leave it unchanged. Wow, that's pretty cool. If not B, then A is equal to false. This expression is identical to this shorthand operator expression. A and equals B. That's pretty slick. You don't need to use this very often, but I just couldn't help myself but to show you. Okay, what did we learn today? Well, we learned about Boolean Zen simplicity. The most often you will use this is if you say if A is equal to B, return true, else return false. That's ugly. Just go ahead and say return A equals B. So that's Boolean Zen. We learned De Morgan's law, which can help us simplify complex Boolean expressions by distributing the bang and flipping all the operators. And we learned about shorthand logical operators. Now that you've seen it all, though, one important thing you need to do, and that is go code, go practice. That's how you need to do it. That's what you will do.